Hello everyone. This is my second video on partial fraction expansion. Basically, in the first video, I explained how to compute the partial fraction expansion when a transfer function or rational function has distinct poles. And I gave example of a transfer function with real poles. In this video, we are going to explain how to compute the partial fraction expansion when function has distinct but imaginary poles. Similarly to my previous videos on control system lectures, I have created a post that explains everything that will be explained in this video, and a link basically to this post can be found in the description below. So here is the post, and everything is nicely written and everything is nicely explained, and now I will try to derive everything what is written over here. If you like these videos, please subscribe or support this channel in some way. So here is the example that we will cover in this video. Our problem is to compute the step response of the following system. So what you can see over here is an ordinary differential equation of second order. The equation is linear, and basically y is the dependent variable and u is the independent variable. So u in our case is a Heaviside function or a step function that looks like this. This is time and this is u of time. So our goal is to compute the function y of t given that u of t is a Heaviside function. So we want to see how our y of t will behave. Most likely it will behave like this, right? Now, what is the physical interpretation of this ordinary differential equation? Well, this can be a simple mass and spring damper system where u is a force, y is the displacement, and these coefficients here 1 and 1, this is a damping coefficient of the damper, and 1 is nothing less than a spring constant. So this is a physical interpretation of the system. So we ask ourselves, when we apply a constant force, how our system is going to behave? How our y, our displacement, will it oscillate or will it stay constant? This is a fundamental problem in mechanical engineering. In order to tackle this problem, we are going to use the Laplace transform. So by computing the Laplace transform of both sides of this equation, what do we obtain? Now, Laplace transform, or this is basically Laplace transform operator of any function, is a linear operator. It means that Laplace transform of two functions x plus y is actually equal to Laplace transform of x plus Laplace transform of y. It is a linear operator for which the superposition principle holds true. So from this equation we obtain Laplace transform of the second derivative plus Laplace transform of the first derivative plus Laplace transform of the zero derivative is equal to Laplace transform of the input. Now, our convention will be if a function in the time domain is denoted by lowercase letters, for example, this is basically y, right, in time domain, in the S complex domain, this will become y of s. So we have lowercase y of time. In Laplace or in the complex domain, this will become capital y of s. So, what is the Laplace transform of the second derivative? What is the Laplace transform of the first derivative? We have to see. Suppose that we want to compute the Laplace transform of the nth derivative of a function y. This notation over here denotes the nth derivative because it's very difficult to write 10 dots, right? It's practically impossible. So we introduce the notation. In this case, this would be first, second, third, fourth, fifth. The notation would be this, right? So this denotes basically, actually this should be 5 here. This denotes the fifth derivative of the function y. Now, what is the Laplace transform of the nth derivative? Well, I'm not going to derive the expression over here, but the expression becomes, you basically write the Laplace transform of y. So, y of time, and this is y of s. Okay. Then you multiply it with the nth power, s to the n power. Then, what do you subtract? You subtract s n minus 1 multiplying what? Multiplying value of the function in time domain at 0. Then you subtract s n minus 2 multiplying the value of the first derivative of the function at 0. And you go on and on and on until you come at s0, or this is simply 1, multiplying what? Multiplying y n minus first derivative evaluated at 0. So this is the expression for the nth derivative, actually for the Laplace transform of the nth derivative. This is a very important expression. Okay, so let us apply the previously explained formula to our specific case. What do we have here? We have the derivative, second derivative of y, and we want to compute the Laplace transform. So the Laplace transform becomes s to the power 2 y of s minus what? Minus s, right? S, value of the function in time domain at 0, right? Minus s to the power 0, first derivative of the function at 0. Good. Let's compute the Laplace transform of the first derivative. Well, the Laplace transform of the first derivative becomes what? Becomes s multiplying y of s minus what? Minus, since here, right, s to the power 0, here is s to the power 1, the next term is s to the power 0, it's 1, and it's the value of the function at 0. And the last term is simply what? Is simply the Laplace transform of y of s. And this equals to capital U of s, equals to the Laplace transform of the function u of s. In this example, we are going to assume that the initial conditions, that is that y of 0 is equal to 0 and that y dot of 0 is equal to 0. So, and then our equation becomes s squared y of s plus s y of s plus y of s is equal to u of s. This is how our ordinary differential equation looks like in the S domain. Now, our next step is basically to make a transfer function and using this transfer function to compute the step response of our system. Okay, so our ordinary differential equation is now let us write this as a transfer function. So what is a transfer function? A transfer function is a transfer from inputs to outputs. It is a rational function defined by y of s over u of s, and this becomes nothing less than 1 over s squared plus s plus 1. So this is our transfer function. Or we can simply denote it by w of s. And our output in the s domain becomes a transfer function times input in the s domain. So this is how our ordinary differential equation looks like in the s domain. It is transfer function times the input gives the output. Basically, you have a system, w of s, you give to such a system an input u of s, you obtain as an output y of s. Okay, now our goal is to compute the step response. In time domain, if your function is equal to the Heaviside function, basically Heaviside function is 0 for t smaller than equal to 0, and 1 for t for time larger than 0, right? Laplace transform is simple. It's 1 over s. Okay, now our output becomes, substituting this expression in the first equation, we have 1 over s squared plus s plus 1 multiplying s. Now, our next goal is to represent this function in the time domain. So we want to see how does this function look in the time domain. This means that we need to compute the inverse Laplace transform of y of s. Now, here comes something what we learned in the previous lecture. How to compute an inverse Laplace transform? Well, the easiest way is to use partial fraction expansion. That is, we can represent this function as what? As c1 over s minus p1 plus c2 s minus p2 plus c3 s minus p3. Okay, and using the formula we explained previously, we can find c1, c2, and c3, where p1, p2, and p3 are 3 poles of this function, right? We can already see one of the poles is 0. And what is now the inverse transform of this expression? The inverse transform of this expression is the inverse transform of all the 3 terms, and then we just sum them up, right? So what is the Laplace inverse transform of c1 over s minus p1, for example? So basically, if we compute the inverse transform of this first expression, we'll obtain something c1 e to the power p1 times t, and c2 e to the p2 power t plus c3 e to the p third pole multiplying time. Now, what is the problem with this derivation? The problem is that basically the poles are complex. So the zeros of this term over here, so what are the zeros? Zeros are minus 1 plus minus square root of 1 minus 4ac This is C, this is A, this is B, right? We remember the formula. This is B squared. 4, right? What is A is 1, C is 1, right? Over 2. So the zeros are minus 1/2 plus minus square root of 3 over 2 multiplying the imaginary unit. And having such expression, you would have to go through Euler's formula. You can substitute these values here. You will have to use the Euler formula, and you will eventually obtain the result. This is I would say, a tedious and difficult way to compute the response. There is a more elegant way to compute this response, and we are going to explain it in the sequel. So instead of following the classical approach, we can compute an inverse Laplace transform of something that looks like this. 1 over s multiplying a constant, let's call this constant C1, plus s squared plus s plus 1 multiplying C2 s plus C3. So we can represent this function, this rational function, as a sum of two terms. Now we have to find these constants. We have to find the constants C1, C2, and C3. If you now go back and watch my first video, I explained the approach, a high school level mathematics approach to compute constants C1, C2, and C3. So let us apply this approach. So what do? We group these two terms together. So what do we have here? We have C1 s squared plus C1s plus C1 plus C2 s squared plus C3 s. Let us group the terms together. So what do we have here? This whole expression in the numerator can be written C1 plus C2 s squared, right, these two terms, plus C1 plus C3 multiplying s plus C1. So this is our expression in the numerator. And this should be equal, from the first expression, this should be equal to 1. Now, when two polynomials are equal, when their coefficients are equal, so we obtain from this equation that, actually we can write this as 0 times s1 plus 0 times s quadratic. So what do we have? We have C1 is 1, right? Then C1 plus C3 is 0. And then finally we obtain C1 plus C2 is 0. So from this system we obtain C1 is 1, C2 is minus 1, and C3 is. Okay, so we have seen that we can represent y of s that's equal to 1 over s multiplying s squared plus s plus 1 as 1 over s plus minus s minus 1 over s squared plus s plus 1. So let us write this as follows. Now, let's call this term y1 of s. And let's call this term y2 of s. So, y of s is equal to y1 of s plus y2 of s. Consequently, inverse Laplace transform of y of s is equal to inverse Laplace transform of y1 of s plus oops, an error, plus inverse Laplace transform of y2 of s. Now, going back, since y1 of s is equal to 1 over s, its inverse Laplace transform is nothing less than a Heaviside function. So it's a step function. Okay. How about the inverse Laplace transform of y2 of s? Okay. Now, to compute this inverse Laplace transform, we have to recall a few properties of Laplace transform. So, the first property is, what is the Laplace transform of a function that's basically scaled? So let's say we have some function f in time domain, and we scale such a function by a constant a. Okay, so what is the Laplace transform of a scaled function where a is a constant? Well, now I'm going to go back and to show you my post. If you have a function f of at, its Laplace transform is 1 over absolute a f s over a. So if you substitute it here, you would obtain it's 1 over absolute a multiplying f of s over a. Okay, why this property is important? Now, in my previous post, I showed you how to compute Laplace transform of a sinus and cosinus functions. For example, Laplace transform of a cosinus function is s over s squared plus 1. Laplace transform of a sinus function is 1 over s squared plus 1. Now, let us see what is the Laplace transform of sinus at. Now, by applying this formula, it is equal to 1 over absolute a multiplying what? Multiplying, we are substituting the values over here, 1 over s over absolute a, actually not absolute a, it's s over a squared plus 1. Now, this expression can be simplified as follows. What do we have here? We have a over squared, right? S squared plus a squared. Now, under some mild conditions, I don't want to go too much into details, we can just, so basically this square here and this absolute value, actually 1 over a in the absolute value is cancel each other. So we have a over s squared plus a squared. Now, similarly, you can compute the Laplace transform of cosinus at. So the Laplace transform of the cosinus at, I'm going to go back to my post. The Laplace transform of the cosinus at is nothing less than s over s squared plus a. Plus a squared. In order to complete this example, we need to recall the second property of the Laplace transform. So we are asking ourselves, if we have a function in the complex domain and it's shifted, what is its time image? What is its inverse Laplace transform? Well, there is a theorem saying that this is in time domain, or if you compute the inverse Laplace transform, this is nothing less than e to the power minus at f in time domain of t, where f of t, if we compute a Laplace transform, is f of s. So if we shift a function, in the time in the frequency domain, right? If we shift the function frequency domain in time domain, we will obtain e to the minus at. So this term e to the minus at is a famous term that appears in ordinary differential equations, in solutions of ordinary differential equations. Now, let's see what happens here. If we would have, let's say, a over s plus some b squared plus a squared in the complex domain, what is this in the time domain? Well, what do we recognize here? We recognize that basically this is nothing less than the shifted, right? Shifted in the frequency domain Laplace transform of the sinusoidal signal. So in the time domain, this becomes e to the minus bt times sinus at. Similarly, if we would have s plus b over s plus b squared plus a squared in the time domain, this is nothing less than basically e to the minus bt cosinus at. So this is basically a Laplace transform of the cosinus function that's shifted in the frequency domain. Okay, now let's recall our original expression. So we had y of s is equal to 1 over s minus s plus 1 over s squared plus s plus 1. Now, we're going to use these two expressions to compute the inverse Laplace transform of this term. So how can we do that? Well, the first idea is to transform the denominator such that it looks like something like this. So how can we do that? Well, we can do this very simple, in a simple manner, right? We can just write s squared plus 2 times 1/2 s plus what? Plus 1. And this is equal, let's complete the squares. This is equal 2 times 1/2 s plus 1 over 4 plus 3 over 4. So this becomes s plus what? Plus 1/2 squared plus 3 over 4. Great. So let us write the original term s plus 1 over s squared plus s plus 1 as follows. We can write this term as s plus 1/2 squared plus, let's write this term as, the last term, as square root of 3 over 2 squared. Okay, now we can recognize b. Here is our b. Here's our b, it's 1/2. And we can recognize RA. RA is square root of 3 over 2. Now, so what do we want here? We want to create, first of all, in the numerator, something that looks like s plus b, such that we can directly apply this formula over here. So let's write down this term as s plus what? Plus 1/2. Plus 1/2. Okay, and let's separate these two terms. So if we separate these two terms, we have s plus 1 squared 2 plus square root of 3 over 2 squared plus what? Well, we want to make sure that we have in the second term, right? In the second term, we need to have a on top. So we need to have this is our a, right? So we're going to put 1 square root of 3 over 2 in the numerator. And what we're going to do, we're going to put here 2 over square root of 3. And then we're going to multiply it by 1/2, since we have 1/2 here. Okay, so this is our original expression. So here is our function written again, right? We have shown that we can decompose this function as a sum of two terms, the first term and the second term, right? Now, we have also shown that we have a basic relation between function shifted in the frequency domain and its time domain image, right? And we have derived these two formulas. So by applying these two formulas to this term and recognizing that here b is 1/2 and a is square root of 3 over 2, we would have that inverse Laplace transform of s plus 1 over s squared plus s plus 1 is the inverse Laplace transform of the first term plus the inverse Laplace transform of the second term. Now, applying the formula, what do we have for the first term? For the first term, we have e to the minus 1/2 time, right? Cosinus square root of 3 over 2, right? Time. This is the first term. What is the second term? Here is our second term. If we have plus 1/2 multiplying square root of 2 over square root of 3, what do we have here? What do we recognize? So here we actually made an error, or we didn't make an error. Okay, so basically, is this correct? Yes, this is correct. This is correct. Only I made an error here, right? So what do we have here? We have e minus 1/2 t times what? Times sinus square root of 3 over 2 times time. Okay, now if you recall our original expression, so our original expression was y of s is equal to 1 over s minus s plus 1 over s squared plus s plus 1. So by applying everything what is written in this slide and in the previous two slides, right, we can obtain that this is equal inverse Laplace transform of 1 over s minus inverse Laplace transform of s plus 1 s squared plus s plus 1, right? So the first term here is nothing less than a Heaviside function. The second term, we can write the second term as minus, we can take out e to the minus 1/2 time, right? What do we have in the brackets? We have cosinus square root of 3 over 2 multiplying time. Don't forget the time. Now, what do we have here? These two terms can be simplified. So what do we have? We have plus 1 over square root of 3 multiplying sinus square root of 3 over 2 times time. And we will add here a Heaviside function, since we don't consider functions for time smaller than 0. So that's, we multiply all the expressions by Heaviside functions. Okay, so everything what you have seen over here in this slide is actually given in the post I've wrote. Okay, so these are all the expressions. This is the final expression. So let's compare. 1 minus, okay, I just wrote it here a little bit differently, right? I've wrote it a little bit differently, but if you take out e to the minus t2, you have cosinus plus 1 over square root of 3 sinus. And this is actually what you can see over here. And then at the end, I also show you how to do this in MATLAB. And here is a simple MATLAB code, how to do that. You define a symbolic variable s, you define a transfer function, you say factorized, you do partial fraction, that you compute a partial fraction expansion, and you do inverse Laplace transform. So if this is your function, this is your factorized, and this is your answer, what you get. Okay, so this would be all for today. Thank you very much for your attention, and if you like this video, please subscribe or support this channel in some way. Thank you.